So, section 13.3, entropy, enthalpy, and free energy. So, the first variable, delta S. Delta S is the entropy. And the entropy, in a very specific way, can be known as the disorder of a system. So, reactions want to have increasing disorder. They want to have more freedom to do what they want. And so if you have a reaction that converts 2 molecules into 3 molecules, you now have more disorder. It's kind of like if you had 2 kids versus 3 kids. If you have 2 kids, is there a lot of disorder? Yeah. Is there more disorder if you have 3 kids? Oh yeah. So, weird explanation, I know, but this can kind of be thought about if you consider the reaction of N2O4 turning into 2 equivalents. Actually, I'll just write it out. NO2 and then another NO2. N2O4 converts into 2 molecules, increasing the disorder of the system. So a reaction that causes a net increase in molecules increases disorder, and delta S would be positive. A reaction that has a net decrease in molecules decreases disorder, and delta S would be negative. Now, when we talk about increasing disorder, what do you think happens when a solid becomes a liquid? Well, a solid is a very rigid structure, and that rigid structure doesn't have much freedom to do what it wants. It's stuck in that perfectly ordered system. But if you turn it into a liquid, now suddenly molecules can move. They can occupy different spaces. They have a larger ability, basically, to go anywhere or to So, a reaction that causes a solid to become a liquid, well, now that solid that has a very, very rigid structure can now have a little bit more freedom in the individual molecules that make up that solid. So that solid can now, let's say, convert into a liquid, and now those liquid molecules aren't as ordered as they would be if they were in a solid form. So for less ordered, we're more disordered. So a reaction that causes a solid to become a liquid increases disorder. Delta S will be positive. A reaction that causes a liquid to become a gas decreases disorder. Delta S is all right, so section 13.3, entropy, enthalpy, and free energy. So delta S is a change in entropy. And so we usually think that disorder is bad, right? So if your house is disordered, terrible. If your life is disordered, terrible. But molecules love disorder. So disorder is a good thing. We want disorder. So the extent that disorder increases or decreases after doing a reaction is considered an increase in entropy. So let's say, what is more ordered? N2O4 Or after N2O4 reacts, and now we have 2 NO2 molecules. Well, N2O4 is a single molecule, and if I convert it into 2 molecules, that's now 2 things, and that's a lot more disorder than 1 thing. You can kind of think about it if you want in terms of, like, let's say children. If you have 1 kid that you're looking after, won't be too bad, but if it's 2 kids or 3 kids or 4 kids, you're going to lose disorder, or you're going to lose order very quickly. So the more molecules that form, the more disorder there is. So a reaction that causes a net increase in molecules increases disorder, and delta S will be positive, because delta S being positive is good for us, and an increase in disorder will cause an increase in entropy. A reaction that has a net decrease in molecules will have the opposite effect. Whoops, sorry, let's take is out of the equation. A reaction that has a net decrease in molecules decreases disorder, and delta S will be negative. Now, we're talking about increases from the start of a reaction to the end of a reaction. What happens? Which side has more disorder? And that's the better side. If we start with more order and we end up with more disorder, that's great. So think about a solid now. A solid is a very tightly packed, well-ordered set of molecules. And so if I take those well-ordered molecules and I convert them into a liquid, well, a liquid has a lot of freedom. It can move, it can occupy new spaces, it can do whatever. So the fact that I'm well-ordered and now I'm into a disordered liquid is going to cause a lot of disorder. So the conversion, look at me, just constantly having the word is there. This will increase disorder, meaning that delta S is positive. A reaction that causes a liquid to become a gas, well, liquid now expanding and turning into gas particles. Now we are increasing our disorder, we're moving faster, we can occupy more space. Everything about this is increasing disorder. I always think it's kind of difficult to think about, oh, how is increasing space increase disorder? I'll just go back to the kid metaphor here. Would you rather have all your kids in one room, or would you rather have them scattered throughout the neighborhood? So giving them more space to go around, more spaces to occupy, means that we will increase disorder. Delta S will be positive again. And that means, inversely, gas to liquid, decrease in disorder. Liquid to solid, decrease disorder. In both cases, delta S would be negative. So let's just jump straight into the enthalpy. So the enthalpy is just the total change in heat for a given reaction at constant temperature and pressure. So a formula you don't need to know, but it helps kind of explain this, is that delta H is equal to delta U plus delta PV, parentheses. So this has pressure and volume, and this is the change in pressure and volume, but we are at constant pressure. So that just means that this entire variable is equal to 0, and simply delta H is equal to delta U. But what's delta U? So delta U is the change in internal energy. So in these cases, the enthalpy is just going to be the internal energy, or the change in enthalpy is the change in internal energy. So if I take A and I convert it to chemical B, I'm not going to really focus too much on, did A have more internal energy than B? Not really too worried about that. The way I'm going to determine that is the surroundings. So when we talk about surroundings, we have two components to a system, to like the reaction that we're doing. we have the actual molecules that we're talking about that are doing the reaction, and that's called the system. And then we have the surroundings. The surroundings is just going to be the beaker they're in or the solvent they're in. Who really knows? And we are going to determine this if this reaction A to B is got a positive delta H or a negative delta H based on the surroundings. And how? Well, the answer is we are going to say, okay, does A have high or low energy? Well, let's say if it has high energy. And let's say with that high energy, it converts to B. And B has low energy or low internal energy. Well, energy can't be created or destroyed, so where did that energy go? Well, that energy that I lost as I converted A to B is going to be released, and it's going to be released as heat. And so where does that heat go? Into the surroundings. So a reaction that releases heat into the surroundings is exothermic. And releasing heat, if we're talking about the internal energy, releasing heat isn't good for the internal energy. So we have a decrease in internal energy or a decrease in delta H, which means delta H is negative. At the same time, a reaction that takes in heat means that we are now adding more energy to our system, which means we have a larger delta U and a larger delta H. So a reaction that takes in heat is going to take in, so it's endo or endothermic. Delta H is positive. So now we get into delta G. So delta G is just the total overall energy change that takes place during a reaction. And so what it's actually going to tell us is if a reaction happens spontaneously. So basically, spontaneously, if you don't know, it's just when a reaction can just happen. I don't need to add energy, any kind of stimuli, increase the pressure, who knows. I can just literally set the molecules there and they'll just spontaneously turn into products. So why is delta G such a big deal? Well, it is a man-made unit that is literally just going to do one thing, and that is going to relate delta H to delta S. So why is that important? Delta H doesn't tell us whether something is spontaneous if a reaction happens. It can tell us if something favors spontaneity, but it itself doesn't determine if something is spontaneous, just like delta S. Only the relationship and the accumulation of both the delta H values, the temperature value, and the delta S value will tell us if a reaction is actually beneficial or not. And so a reaction that requires a net consumption of energy is going to be Exergonic. And what does that mean? It means that it needs energy in, and delta G is now positive. We have an increase in total energy in our system, which isn't good. It means we're not spontaneous. Now, a spontaneous reaction requires a net release of energy, and that's great. No molecules like to be really high energy. They like to be as low energy as possible because the lower in energy they are, the more stable they are. And everyone loves to be low energy and stable. And that is what we call an exergonic reaction. And for that, delta G is negative. Now, what's this third variable? Well, if your reaction is at equilibrium, delta G is neither positive nor negative. It is just 0. So now, a reaction takes place inside of a beaker. After completion, the beaker was cool to the touch. What can you conclude from this information? Well, all we know is that it was cool to the touch. And so what does that mean? If it was cool, well, it's not very hot. I don't know why I left that. And that means that when I say it means that the system, our actual reactants, took in energy, or sorry, took in heat. Get that correct. So if we take in heat, and we're saying heat here, well, this is going to revolve around delta H. And delta H, when I take in heat, is negative, and that is endothermic. So, like we said, delta H is determined by what happens to the surroundings most of the time. So because the surroundings were cool, they lost heat, which means our molecules took in heat, which means they gained energy. Whoopsie. Positive sign. Sorry. Delta H is positive, which means we are endothermic. I like how I caught myself from explaining why I was wrong to myself without even realizing. So the sign of delta H is positive. All right, so now let's talk about the classical equation of thermodynamics. So most people have seen this table before, and it's going to tell you whether a reaction is spontaneous or non-spontaneous based on the cumulative expression of the value of delta H and delta S. So most students kind of think, oh, let me just memorize this table. Let me tell you, I hate it when students memorize this table. And if you are comfortable memorizing the table, I have no problem. I'm just going to show you the way that I usually go about this table. So delta G is in kilojoules, delta H is in kilojoules, and then delta S is in joules. So that means that roughly, if we're thinking about the units here, delta G and delta H are 1,000 times larger than delta S. Not a great correlation or for something for me to say, but I'll explain why I'm saying this in a second. So what I usually do is, to answer these questions about if a reaction is spontaneous or not, I set up a fake problem. And that fake problem looks something like this. So for delta G equals delta H minus T delta S, I know that delta G and delta H are in kilojoules. So I just assign them random values of 1,000 joules each. And for delta S, I assign it a very low number, like 1. So, whoops. What did I just erase? Okay. Minus T, and then because it's in joules, it's like 1,000th of a kilojoule, so I just gave it a value of 1 joule. So, here's the basic setup, and this is assuming everything is positive, right? I know that if I have a positive delta G, a reaction is not spontaneous. I know if I have a positive delta H, I know that means I have a endothermic reaction. If I have a positive delta S, it means I have an increase in disorder. I know what each variable means, and especially I know how to determine if it's positive or negative. That's all you need for this. So let's say, as written, I have all the variables as positive. And actually, let's just say I don't know what this is yet. I'm trying to figure out, is delta G going to be spontaneous or non-spontaneous, or spontaneous at some temperatures, non-spontaneous at other temperatures? That's what this entire table is trying to figure out. What is that delta G? Well, delta G is going to be spontaneous when it's negative. So as this equation set up, is there any value I could have for T that would make this spontaneous or non-spontaneous, whatever? Well, I have 1,000 minus T times 1. So right now, as written, basically, I have 1,000 minus 1. I have an overall kind of positive number here. Now, so that would mean that I am I would have a positive delta G value. And overall, that means I would be non-spontaneous. But if I increase my T value to like 1200 or something like that, I would have positive 1000 minus 1200, which would be minus 200. So I just went from a kind of positive value if T is really small, and then I increased it so much that now my overall value for delta H minus T delta S is now negative. So when delta H is positive and delta S is positive, this bad boy depends on the temperature. I can be both spontaneous or non-spontaneous. It just depends on the value of T. All right, so as another example, let's say I'm talking about an endothermic reaction where T is going to be, or S is going to be negative. So I have a decrease in disorder. Well, endothermic means I have a positive delta H minus T times minus 1. What do you know? 1000 plus T times 1, just canceling out the two negatives. No matter what, whatever temperature T is at, this will always be positive. So a positive delta H and a minus delta S means that delta G is always positive. For my last one, what happens if I have a exothermic, a negative delta H, and then also I have an increase in disorder, a positive delta S? I would have delta G is equal to minus 1000 minus T, then positive S, or sorry, for this example, positive 1. No matter what the value of T is, I'm always going to have a negative number. So delta G is always going to be negative. And so for a minus delta S and a positive delta, or a minus a negative delta H and a positive delta S, my delta G is always negative and I'm always spontaneous. That's the best possible case. A negative delta H and a positive delta S. That's when I have a spontaneous reaction every single time. So I hope that helps. Now we just get into a bunch of practice problems. And I'll just fly through these. Maybe, relative to my own speed. In a spontaneous process, which of the following by definition must increase? Well, that's just a definition from the second law of thermodynamics, the entropy of the universe. And the entropy of the universe is the sum of the entropy of the system plus the surroundings. For each reaction, what is the sign of delta S? All right, so now this is just testing increases in molecules, changes in phase. We have 3 molecules becoming 2 molecules. Well, that's a decrease in disorder, which means delta S is negative. 2 molecules of N2O4, what the heck? That's not right. That's not even balanced. N2O4 becoming 2NO2, that's an increase in disorder, so that's positive. Now I have H2O liquid becoming H2O solid. Liquid to solid, liquid is kind of disordered, and then a solid is very ordered. That's a decrease in order, which means that we are negative. All right, so the next problem. What is true concerning a reaction that releases heat and results in an increase in entropy? Well, we are releasing heat, which means we are losing energy, losing internal energy, losing enthalpy. We have a negative delta H, and we also have an increase in entropy, so positive delta S. And these are asking us again about spontaneity. So we'll have to use delta G for this. Delta G is equal to delta H minus T delta S. Setting up the way that I like to do it, delta G is equal to, we have a negative value, so negative 1,000 minus T, and then a positive S. Well, negative 1,000 minus some numbers is always going to be negative. So delta G is always negative, which means this reaction is spontaneous at all temperatures. Next question, what is true concerning the following endothermic reaction? All right, we have one molecule. It is a solid getting converted to one solid and one gas. Sounds like an increase in disorder to me. Well, we now know that this is positive delta S, and it's endothermic. So we have a take in of energy. So because of those two variables both being positive, delta G is equal to plus 1,000 minus T delta S. We are, oh sorry, I always say just delta S instead of sticking to the way. 1,000 minus, let's say, T. Well, if T is below 1,000, will still be positive. If it's greater than 1,000, will be negative. So, when is this reaction spontaneous? It'll be spontaneous when delta G is negative, and it's going to occur when negative T is equal to negative 1,001 or higher. So at high temperatures, we are spontaneous. At what temperature in Kelvin would delta G equal 4,800 joules, delta H equals 8,300 kilojoules, and delta S equals 50 joules per Kelvin? Now we're getting into actual calculations, not just conceptual. So the number one thing to worry about in this problem is the fact that they gave us delta G in joules and delta H in kilojoules. That's the only real challenge here. So let's turn this all into joules here. So 4,800 is equal to delta G. Delta H is 8,300. We don't know T, and then S, delta S is equal to 50. All right, well, this could be as straightforward as going 4,800 plus 50 times T is equal to 8,300. Subtracting 4,800 from each side gives us 3,500 is equal to 50T. And that means that T is equal to 70. So at 70 degrees Kelvin, delta G would equal 4,800 joules, delta H would equal 8,300 kilojoules, and delta S would equal 50 joules.